Okay, so we're on section 3. We're going to finish that today. So we were talking about set operations. The last thing we were looking at was this problem. So what these series of problems are doing are using specific examples to come up with a conjecture about what there may be some general rules. So sometimes you can, you could derive through some mathematical proof that certain things are true all the time. They're identities. In this case, we're picking one example and we're doing it, and then we're going to make a conclusion or a conjecture from that one example. And it may be true or it may not be true. Most of these are true ultimately, just using one example, but that doesn't guarantee it. So all you have to do in these problems is answer the questions for A and B, and then based on what you see as the results for A and B, make some kind of conjecture about the two. Usually, are they equal to each other? That's usually the, are the two statements equivalent to each other? So if we look at this, it says find what is the union of sets X and Y. So here's the two sets. So if I wanted to know what is the union of those two sets, it would be a set, and it would consist of the numbers. What's the union? Is going to be, so there's two choices. There'd be 1 and 3. That would be one set. Or I could do 1, 2, 3, and 5. So it's either the common terms or it's all the terms combined into one set. So which one is the union? All of them, right? So the union would be 1, 2, 3, 5. So those are the elements that are in both. I want to say both sets. They are in both sets, and you're basically looking at all the elements, possible elements. And if you change the order, it doesn't really matter. If you're comparing X versus Y or Y versus X, the union operation doesn't matter what order it is in. You still are comparing these two sets and saying, well, I'm just going to list all the elements that are available. So I get the same answer. So the conjecture would be that X union Y is equal to Y union X, based on that one example. So and is that always true? Yeah, it turns out, you could use logic to prove that's true, but we've done it using a specific example. So this would be an example of inductive reasoning, where you are looking at a specific example, in this case only one, but if we looked at multiple examples, we would get the same result, and then we'd say, oh, we can make up this rule that we think is true. So there'll be a few more that look like that, and that's how they're done. Okay, next piece of information. There's also a set operation, which we'll talk about in just a second. But if you take two sets and you create ordered pairs from these two sets, the ordered pair is just a list of two numbers, or two elements, element A, comma, element B. It's like the coordinates in a XY coordinate system. So 3, 2, you'd go over in the x-axis 3 units, and you go up to the y-axis 2 units, and there'd be a point. That's an example of a coordinate pair. It's also an example of an ordered pair. The first element, or the first number or letter, is called the first component, and then the second letter, B, is the second component. In general, the order is important. The only time the order is not important if it's the same number. 2, 2 is equal to 2, 2. It doesn't matter which way that goes. But 1, 3 is not equal to 3, 1. The order is important. That's why it's called an ordered pair. Okay, so you guys have a lot of experience with that. So you got a couple of problems where they ask you whether these are true or not. The statements are true. So in this case, we do the math inside the parentheses. Let me put that on one slide. And the answer would be, the first one would be, yeah, it's true, because 5 minus 2 is 3, and 1 plus 1 is 2, which is the same result. So in this case, I would say it's a true statement, because they're the same numbers and they're in the same order after you do the math. Now the second one, which I'm going to pull up so you can see it better, this one's just asking you whether order is important or not. There's no calculation to do. They're already numbers. So is 2 comma 13 equal to 13 comma 2? And the answer is no. That's a false statement. If it was a set, if they had little curly brackets, 2 comma 13 would be the same as the set 13 comma 2. But when it comes to ordered pairs, the order is important. So this would be false. So I think I assigned 1 or 2 of those problems. They're not really too excruciatingly difficult or anything like that. So the set operation that we're talking about here is called the Cartesian product of 2 sets. So let's put this on one page. So the definition of the Cartesian product of 2 sets is A cross B equals the set of the ordered pair A and B such that A is an element of set small a. The element A is an element of the set A, and the element B is an element of set B. Basically what you're going to do is you're going to make ordered pairs where the first number is from set A and the second number is from set B. So it's just easier to give you an example to show what this means. So I'm going to do it on this page. Let me move this up so it's almost out of the way. So let's define set A as 2 numbers. And they don't have to be numbers. They can be anything really. So set A consists of the 2 numbers 1 and 3. Set B consists of the 2 numbers 2 and 4. So the set operation A cross B is, it's a set, so we put a curly bracket. It consists of ordered pairs, so we're going to have an ordered pair. We're going to take the first element in the ordered pair, the first term in the ordered pair is either going to be 1 or 3, and the second number in the pair is going to be either 2 or 4. So what you do is you take your first number in A and you create 2 ordered pairs with the second number being the 2 choices from the second set. Then you take the next number. Once you've done that, in this case we have 2 options, we change the first number in the ordered pair to be the second element in set A, and then we do the 2 numbers in the second set. So that's what cross product or Cartesian product means. You just end up with 4, in this case 4 ordered pairs. They're a set of 4 ordered pairs. And the number of ordered pairs is going to be the number of elements in this set multiplied by the number of elements in that set, which is 2 elements times 2 elements is 4 elements in the Cartesian pair. Cartesian product, sorry. So let's look at one more example. I usually put one of these on the test, so make sure you know how to do it. So here we have the numbers A. Set A is the numbers 3, 6, 9, and 12. Set B is 6 and 8. So since we have 4 elements and 2 elements, 4 times 2 is we're going to have 8 ordered pairs. So A cross B is a set. We take the first number in the pair to be either 3, 6, 9, or 12, and the second number to be either 6 or 8. So we'll take the first number here do the two numbers in the second set. So that's 2 out of 8. Then we change to the next number, 6, and then we take that second number and we do it twice. So 6 and 8, and then we go to 9, the next number. So the first number is 9, the second number is 6 and 8. And then finally we take the last number in the beginning, which is first set, which is 12, and again 6 and 8. And that's the answer. Now if you do B cross A, you're still going to have 8 pairs, but they're not going to be the same. What we do now is we let the first number either be 6 or 8, and let the second number be either 3, 6, 9, or 12. So here we had groups of 2 together. We had 2 associated with this, 2 associated with that, 2 associated with that. In this case, we have 2 choices for the first number and 4 choices for the second number. So we're going to take this 6 and then do each one of these 4. So we'll do 6, 3, 6, 6, 6, 9, 6, 12. So that's 4 of them. And then we change the first number to the next one. So we take 8, and then we cycle through the 4 second numbers. Not how I've listed them here, but how they're shown in the operation. So you get 8, 3, 8, 6, 8, 9, 8, 12, close set. So let me add a page here. Bring this up. So I want you guys to. We'll just do one of the 2. So let's do A Cartesian product B. How many pairs will there be in that set, the resulting set? Remember what I did is I took the number of elements. Yep. So it's 3 in this one times 3 in that one gives you 9. There'll be 9 elements in the set consisting of the Cartesian pairs. And these are just letters. It just happens they spell a word, but that's not necessary. So I'll help you start the first part. So that'd be the first 3. So there you go. Hopefully that's what you got. Okay, moving onward. Okay, so we've already used this rule. I'll put it up on the board. I'll give time to people to finish this one. But basically, this is how we figured out the previous question. If you have 2 sets of so many elements per set, the cardinality, remember that's the number of elements per set, the resulting number of elements in the Cartesian pair is just the number of each one multiplied together. Okay. Okay, what we're going to do now is we're going to do some stuff with Venn diagrams. This is in your book, so don't try to write it down. This is kind of a review of what the simple set operations that we've dealt with so far. So this is the definition of the set operation. This is the mathematical description. And this is what the Venn diagram looks like. And the light blue area is the area that they're talking about. So you have all these rectangles are the universal set. Within the universal set, you can have a set A or set B. In the case of the complement, the elements that are in set A would be inside here. You'd have them written out. Therefore, everything that's not in A but is in the universal set is what this light blue represents. So the light blue represents the complement of A. The complement of A being the set of elements that are in the universal set but not in A. So that's how you do it graphically. The intersection, we have two sets, and some of the elements in the two sets are in common. So the overlap area between these two sets would be where you would have the elements that represent the intersection. Yeah, this is highlighted right here. It's in your book, you'd be able to see it better. It's kind of light green and light blue. So the union of two sets consists of all elements that are in both in set A and set B. You do have some common elements, but you only write those down one time when you show the union. So if there's overlap, if there's commonality between the two sets, you don't write them twice, you just write them one time. And the difference between two sets is, the difference between set A and B is this circle would represent the elements that are in set A. When you subtract something, you remove the elements that are in set B, also in set B. So we take out this area. We're basically subtracting the intersection. This represents the intersection. So to get A minus B, you take the elements in A and you remove the intersection, the values that are common between the two. And we're just going to ignore that right now. Cartesian product, that's just the definition. So this is just a summary of the definitions and what the corresponding Venn diagrams are associated with. So we're going to look at some more complicated versions of Venn diagrams here. So you're going to end up doing this, but we're not going to do this all at one time. What this represents is the intersection of set A and the complement of set C, and then union that with B. Okay, so that initially looks very complicated and you're ready to give up, but the thing about math is you've got to do things in nice bite-sized pieces. If we go back to the work we did the other day, where we looked at these kinds of expressions, we couldn't just look at it and say, I know what the answer is. We had to do the stuff that's in the parentheses. If we had a complement, we had to do that first. So we did the same thing with Venn diagrams. And when we do that, we'll understand more about what's going on here. So what I'm going to do, well, I'm going to clone that thing. I'm going to drag it over here. So just like we did before, rather than doing this whole thing, the first thing that we have to do is figure out what is the complement of C, where this is set A, this is set B, and this is set C. So we can go back to our list of, if you have your book, you could keep that open, but this was the complement. And I don't have any way to highlight it, so what I'm going to do is I'm just going to use some different colors to put lines to represent these various operations. So the complement of C, the way I do that is I just take this pen and I make diagonal lines, and as long as I'm out of C, I just keep going. But when I get to C, I jump over to the other side and then I continue on. Pardon me? The upside down, oh, this means intersection. This means union. So the complement of C is everything that's in the universal set, which is the rectangle, but not in C. So that's what C prime stands for. So you'll notice there's no blue lines inside of C. Okay, so let's trying to get this thing. Drag. Oops. Let me add a page. Okay, so that's the complement of C. Now, let me group that all together. Group and clone that thing. Okay, now, so I'm going to take what I just did, which is the complement of C, and I'm going to do the next operation, which was intersect A. So I'm going to do A intersect C prime. So I've already got C prime now. So I'm going to use a different color, and I'm going to represent this set, and then I'm going to look at the operation. So I'm going to use red, and I'm going to do it in this direction. This is the red lines represent set A, everything that's in set A. So you can see on the diagram, there's some places where there's just blue, there's some places where there's red and blue, and there's some places there's only red, and there's some places that don't have anything at all. Okay. What this operation, the intersection, represents is where you have common things happening. So common means I have both of those kinds of both colors together. So this operation intersection, I look for places where there's blue and red. So here I have just red, so that's not included. Here I just have blue, so that's not included. Here I have blue and red. So I'm going to kind of use another color to show the whole result. So this is, if I color in what's both blue and red, I'll get this part right here. So that green represents A intersect C complement. Now before we go on, let's go back to this screen. Compare what that looks like with what we just did. So they look kind of the same, don't they? This looks like A, and I'm subtracting what I have in C. So it turns out this is a statement that's always true. If you have A intersect the complement of C, that's the same as taking set A and subtracting what's in C. It turns out that's a lot easier to do than what we just showed here. We'll use that in the future. So A intersect C complement can be replaced with A minus C. So we've proven that one time it always works. We'll use that in the future just to make our life easier. Okay, so now the last thing we do is we're going to take this little green thing and we're going to do the union with B. So let's see how that works. So what I'm going to do is I'm going to go to the next page and I'm going to go ahead and mark this in again. So I'm going to use, so this green is A minus C, which is the same as A intersect complement of C. Okay, so green is A intersect C prime or A minus C. Now B, set B, which is the other thing that we're doing here. There's B. We'll show that on the. We'll show that B. This is A. This is B. This is C. So if I want to represent what's in set B, I'll just show it by blue lines that are going all across set B. So B is blue, right? So my operation of A intersect not C union B, what that's going to be is it's going to include not the overlap, that would be intersection. So if I did the intersection, it would be this little part here, but the union would include everything. Would include this plus that. Everything that's colored in would represent the union of this area and that area. So I can use, what color haven't I used here? Red. So this whole final operation is going to be basically everything that I've got marked. So when you have an intersection, you look for overlap. When you have a union, you just basically have everything that you have marked up. So that would be the final answer. Okay, so that's how it works. Okay. Let's look at another. We're going to do a few of these because it's not obvious the first time you do it. Okay, so here we have the complement of A intersect the complement of B intersect C. Again, depending, in math you want to make things as easy as possible. So one thing we've done to make things easy is we can use this result. The second result is if all of these operations are intersections, which happens a lot. The order is not important. So I can write this as A, complement A, intersect complement B, intersect C, or I can write it as C, intersect complement A, intersect complement B. I've just changed the order. There's two complements and one that's not a complement. So, to do what's in the parentheses, A intersect complement C intersect complement A is the same as C minus A. So I used my second. So one thing I can do is I can change the order to make things easier. It's always best to start off with something and then subtract things from it. I can also replace the thing in the parentheses with C minus A. And I can also do the same thing for the second part. So instead of having the intersection with the complement, I can just subtract stuff. So you'll get this in a second, don't worry. So what I do to find this particular result is I would take set C like this, so that's this part. I would subtract what's in A, also in A, so I just find out the common area between the two, and then I subtract B, and that's my answer. So if you remember what I did in this previous one, I had to do all this stuff outside of circles and find the overlap, and it was very difficult. But by using these simplifications, I can fill in one of the circles and then just erase the stuff that is the subtraction, and I get the answer. So it's a much easier way of visualizing it. You could go through the long way and find out what the intersection of these two complements are, and then but you get so much stuff overlapping, it's really hard to understand. Okay, we're going to do mostly these kinds of problems, which turn out to be not that hard. So let's look at another case here. In this case, we can we could either do it in either order. Usually if you have a complement, a lot of times putting it last is the easiest thing to do. So we'll do it both ways. So we're going to show it doing this way, and I'm also going to do A intersect B and then intersect C complement there. So we'll show you how you do those and how you get the same result. We'll make a decision whether one's easier than the other. So I'm going to move that down there just so you know. Okay, so let's just do it in the order that's shown. So A intersect not C, what's the equivalent of that? A minus C, right? So if I take A and I subtract C, all I have to do is I'll take A, so I'll color this in, and then I'll erase what is in C, or I can just put it in and erase it, or I can just show the results. So I'll do them both ways just to show you how this works. So if I did it where I color in A, and then I subtract what's in C, I'll get that, okay? Or I can just think of it, it's A minus C, and I just color it in. So either way, you can think about that. So that is the first operation. What does it mean? Or yeah, the complement of something is back here. So if I said, if I wanted to know what the universal set is, I just color everything in. So that's the same thing. C prime? Yeah, C, so yeah, C prime is everything that, but what I did in this case is instead of doing A intersect C prime, I just did A minus C. They give you the same result. So that's what I did. I took A and then I erased C to get this result. Yeah, let me just show you what it would be. If you did it without using the subtraction thing, the way it would work is this would be A, and the complement of C would be everything except what's in C. So it's everything outside of C. So the red is the complement of C. So I'm just drawing lines until I run into C, and then I skip over top of it. So that's the complement of C. And then the intersection of A with complement of C is where you have both the black lines and the red lines, which turns out to be this little sliver. So it's the same as taking A, subtracting C is the same as A intersect complement C. So that's why once you understand that, it's better just to fill in A and then erase the little part instead of having to draw lines for the whole thing. It just gets crazy. Okay. Erase that stuff. Okay. So the black part is A minus C. A minus C. When I do this, it means I'm erasing. Okay. So I'm filling this in and then I'm erasing C. Okay, the second part is the intersection of A minus C and B. Well, intersection is the overlap. So what part of this, if I can fill it in, let me just do that, and then we'll again figure out how to do it without having to fill everything in. So that's set B, everything that's in the circle. So what area has both green lines and black lines? This little part right here. Yeah, it's that little part right there, but not this part. This has green, this has black. So it's this little shield area. So that is what is A minus C intersect B, is this little shield. Now, if you didn't want to fill it in, the way you would do it is you would say, okay, this area here is A minus C, because I have A minus erase C. And then I'd say I have the intersection with B. Well, what parts of circle B already have black lines in it? Well, this part does. The rest of them don't have any black. This would be A intersect C, but this part's not filled in, so I don't want to include that. So I could immediately say that this, which is the black lines, intersect B is just this little area that's in B, but is also contains some of the black lines. So that's the answer. Okay, now let's do the same thing here, but let's do it in a different order. So A intersect B, let me draw a little underline here. So A intersect B is the overlap between the two. So it's a little football. So footballs are intersections of two sets. So I've done that. Then I subtract C. That means I erase the area that involves C, which leaves me with the same result. So whether I do it in this order, A intersect not C, which is the same as A minus C, which was this black area, and then find the intersection with B, I get that. And if I do it the other order, I get the same answer, but in this case I had a football, which was this part, and I subtracted what was in C when I did intersect C prime, which is the same as minus C. Okay, let's do another one. Okay, let me make one up. It's not exactly what we've done here. So let's take A intersect B complement intersect C. So what we would do is we would say, okay, this is set A, this is set B, this is set C. So A intersect B complement is the same as A minus B. So A is this, minus B, you take this part out. So A minus B, which is this part, is what's in A, but that I've subtracted out what's in C. If I filled in A completely and then erased B, I'd get that result. So that's A minus B. Then I want to intersect that with C. So I look at C and I say, okay, what parts of C are already marked? Well, just this little bit right there. So if the final thing, so this is A minus B. If I take A minus B intersect C, I'll end up with this little bit right there. It's the part that I started with, and then find the intersection with this circle, which is this little bit right there. So this is A intersect B minus C. This is A intersect C minus B. This one would be this little shield part here would be B intersect C minus A. So these three little shields are the result of intersecting things and then erasing part of it. Here I'm intersecting A and C and I'm erasing B. Here, if I did this one, this little area would be B intersect C minus A. Okay, let me clone this thing. Clone. What about this little area right there? Anybody have any idea what that is? So that's A intersect B intersect C. That's the part of the graph where all of the circles overlap. It's this little shield in the middle. So we know what these four places are. We know this and this and this are an intersection and then subtracting off. So you have two sets intersecting and then intersecting with the complement. Those are the three little areas here. This middle part is the intersection of all of them. This football here is A intersect B. This football here is A intersect C. And this football is B intersect C. If we take, then we've got this little bit that's right out here, which we haven't talked about yet. Anyway, we'll come back to that. I don't want to get. So you got those for your homework problems. You basically have to show the Venn diagram and go through these operations. Okay, now we actually used this just a second ago. Well, we didn't use this particular one, but there are some rules that apply that are good for all sets. And this one relates the complement of an intersection with taking the union of the complements. And then you've got the opposite here. You've got the union of two sets taking the complement is the same as taking the complement of each and doing the intersection. And just like we were able to make a substitution saying A intersect the complement is the same as A minus the function, that was a rule. Here are some additional rules that you might be able to use to make it easier to answer questions about set operations. There are equivalent ones for logic, which we'll talk about in Chapter 3, which are used in computer circuits. You can design computer circuits to perform operations like intersections or unions, but some are much more easily built than others. So what you do is you use these similar type of laws to substitute circuits that you can't build with circuits that you can build. And so it's a very useful thing in computer design. An equivalent. You'll see it again in Chapter 3. We won't actually use this right now. What I want you to try to be able to do is visualize these operations on a Venn diagram. Okay, so I'm just introducing those. Okay, the other way is to look at the Venn diagram and try to come up with what the set operations were. So we just did the set. Our operations came with the diagram. Now we have the diagram. We're going the opposite way. So what we have is this light blue area. And what we try to do, there's multiple ways of answering the question. We want to come up with the easiest way of answering the question using what we know. So I'm going to ask you guys a series of questions, and then we'll come up with the answer. So the white, what we're interested in is the blue area. But if we wanted to say, what does the white area represent? So is there a set operation, A intersect B or A union B, that is represented by the white area? It's one of those two. So yeah, it's the union, right? Because A intersect B would be this area. A union B would be everything. So if this is A union B, then what is the light blue area? Pardon me? Who said that? Who was the... Oh, okay. What'd you say? No. What haven't we used? Union prime, yeah. So the light blue would be the prime of A union B, right? So if the white is A union B, then everything outside of there has to be the complement of that. So that's the answer, okay? So we looked at what we knew. We know that the white, I'll write this out, the white is A union B, therefore the blue is A union B complement. So if you can figure out what something is, everything else is the complement. It's the set of, this complement is the set of all elements that are not in the original statement but are in the universal set, which means it's everything in the rectangle that's not originally contained. So that's the answer. So let's go look at the next one. So if we were to say if we made everything green, just like we did over there, what would be if this were also green, what would that represent? Jackson, Red Sox. You got it right in that last time, so I'm counting on you to do it. Right, so well, what does that represent? The intersection. So what you do is you take the whole thing, which is A union B, and you'd subtract A intersect B. And that's the answer, okay? So what we do is we look at, something we know. We know intersections and we know unions. So if I were to make everything green, so let me just do that first. So everything's now green. So green is going to be A union B. Now, the white, so that's green, all green, meaning I've filled it in. The white, before I filled it in, the white between the two. Okay, so this little white football, the white football, that is A intersect B. So the blue, which is what we're trying to figure out, is going to be A union B, which is everything that's in A and B, subtracting A intersect B. Okay, get that? See how that works? So it's a matter of, it's kind of by subtraction. We do this later in geometry. You know, a lot of weird areas, they may be a weird shape, but a lot of times you're able to take shapes that we know, like rectangles and circles and triangles, and come up with what the area, the weird shaped areas, because you can subtract. You can subtract a triangle from a circle to get some shape that we don't really have any information on. Okay, so let's try another one here. So again, we're trying to figure out what the orange area is. So what if we figure out what the white area is and then take the complement of it, right? That makes sense. So what is the white area? It's A, what's that? Well, A prime would be all this stuff outside the area. So we're taking A, we're looking at the white area. So we have A, and we're getting rid of this. What does getting rid of mean? Subtract. Yeah, well, the A intersect complement B, or A minus B. A minus B is the easy one. So the white area would be A minus the stuff that's in B. It's that little moon shape. If I had over here, this area would be B minus A. This is A minus B. This is A intersect B. All of it is A union B. Okay, so this is A minus B, the white area. So the orange area has to be A minus B complement. Let me write that down. So what I'm doing is I'm taking set A, which is everything in here. I'm subtracting B, which gets this part out, so that just leaves me with the white stuff. And then I'm taking the complement of that, which means it's everything outside of that little moon shape. We already know the answer to this one. We just did it, right? It's afterwards. So what is this? We just did it. A minus B. So we took everything in A, we subtracted what's in B. So this little bit here would be B minus A. There's a couple of ways of doing this. What does this football represent? Yeah, A intersect B. What does this football represent? Okay, so if I wanted to include everything in both of them, what would I use? The other one, right? The union. So this football is A intersect B. The other football is A intersect C, and I want to include everything, so then I would do a union of the two. So again, we're breaking it up into little parts and then constructing it back together. So this part here that is A intersect B. This area here is A intersect C. The whole thing, all of this stuff, which is what I'm looking for, is going to be A intersect B union A intersect C. And there's probably, like I said, there's probably more than one way of doing it. But that's probably the easiest way of doing it. Okay, let's see what I got here. Now this one, if you think about it, is very similar to this. This is A minus B. So what do you think this little sliver is? Yeah, so what you would do is it's A. So if I did A, it would be the whole thing. Subtract B, and then subtract C. So again, if I filled it all in with red to start with, that would be A. Subtract B would take this part out, which would leave me with that part. And then subtract C, what's left over, leaves me with that. So all these little corner pieces, this is B minus A minus C. This is C minus A minus B. This is A minus B minus C. So let's review. The center is the intersection of all of them. These footballs are intersections of two sets. A and B would be this football. A and C would be this football. B and C would be this football. All these parts that are out where it's just A is A minus B minus C, which is probably the same as A intersect B prime intersect. I'm using that identity the other direction. So I did it one way, so there's no reason that I can't do it the other way. Okay, so anybody want to take a guess at what that is? Maybe not a guess, that's educated approximation. So it's this little bit right up here. Very good. Yeah. So why is that? Yeah. So if you A intersect B, you get that football. If you subtract C out, you erase that part and leaves that. So this one's going, let me write it down, and then we can talk about this three other similar looking little pieces. This would be, it's A intersect B, which is this whole thing, minus C. Or it probably would be A intersect B intersect C complement, the other way looking at it. Anyway, so this part, this would be A intersect C minus B. This would be B intersect C minus A. All of them have the same kind of setup. It just depends upon which ones define the intersection. Okay. So there's the homework. We'll come back to this one in just a second. So you can go ahead and write those down. So it's fair. There's a fair number of examples, but there was a lot of material we covered in that. We haven't had any assignments for quite a few days, so. So this is due next Monday. I know. Okay, so somebody other than Jackson Retzloff is going to answer the next question. He's got it down, so he's on a roll. Yeah, he's going to get an A on the next test. Okay, so think about this again. Think about if I were to, what would be the first step? Is I want to do something that's fairly simple, that includes sets B and C. So which would that be? The union. So that would be everything in B and C. So that would include this, and it would include that. So how do I get rid of that part? Simpler than that. So you're going to take, yeah, so just subtract A. So what you do is, I'll use a different color here. So B union C would be everything in A and everything in B and C. So that would include all this stuff and all of that stuff. To get rid of this part that I just marked in, all you'd have to do is subtract A. So the answer is subtract A, which I guess would be the same as intersect A complement again. Okay, well, we finished that section, so that's good. We'll move on to section 4, which is similar to it. It's talking about surveys. You know, do you like this and do you like that, and how many people like this and that, and it involves intersections of various things. So it's an application of what we just talked about, and more specifically, you know, how many people like something. It's associated with numbers instead of just visually what we're talking about here. We're talking about intersections. We want to know how many people like one thing and another thing. So it's basically analyzing surveys. And that's the end of chapter 2. But we won't have a test yet. We're going to do part of chapter 3 before we take a test. Yeah, let me make sure nobody came in late that I didn't get. I think, oh, James, yeah. Put a late on you. Yeah, just one second. Let me get